Good morning, everyone. My name is Busoy Okwegbemi Matthias, a five-year student of Electrical Electronics Engineering in the University of Ibadan. I'm here to walk you through my undergraduate final year project setup, which is on impact of Prosumer operations and optimized load management on peer-to-peer energy trading in a distribution microgrid network with short-term PV power forecasting. So the project is divided into two phases: the PV forecasting, PV power forecasting, and the optimized load management, which uses a non-trading setup as the baseline and then compares the result with when peer-to-peer is integrated into the network to see how improved the loss of load is, which means how minimized it is, because the goal is for us to minimize the loss of load. So for the peer-to-peer energy and for the PV power forecasting, the first step was in terms of getting the data set. So data set was gotten from a previous research, which was a work done by a person at all. So it's a freely available data set. We had to firstly imported unnecessary libraries, then opened a CSV file that contained data set. Then we did a bit of exploratory data analysis to understand what the data contains in terms of building a model. So variables of the major features of the data were the longitude and latitude, which are things we don't want to be model to be very independent on. Things like cloud cover, pressure. So both um, geological data, temporal data, historical data were included in this data. So historical data includes the pipe power in itself, which is a trend of how a solar panel generates or how much power it generates over the period of time, right? Then things like humidity, ambient temperature, wind speed. These are things that are the weather conditions of that environment, which can determine or affect the amount of power that is generated by that particular PV system. So this was to get a bit of statistical understanding of what data set contains, right? So this is a bit of exploratory data to see if the data is clean. So from this, you can see that not every no, the data is clean and contains null value, but we still have to do some exploratory data to confirm if there are no outliers and the like. So we did a bit of that, got statistics and all, right? So there was to understand how the data set is. I did a bit of confusion and correlation matrix to see the linearity of each of the feature which with the piper, which is what we're trying to determine, and to get a bit of understanding of it. So we can see that cloud seeding and pipe power have a very good relationship of 0 point 0.4 linearity. I mean, this is quite intuitive, seeing that the cloud covering should affect the power, because if the more covering that there is, or determines how much sun is hitting the sun, therefore ends the conversion. So that this is a ways to get intuition behind what what data set is saying. Right, so I did a bit of variation. I did a bit of variation. Sorry. So seeing the image of the so this is a trend line of the data set with time, which is the pi power. Excuse me. So it's a trend line for the so showing the how the data varies with time. You can see a sort of trend pattern here with season for the data, right? So we continued by some of if we look closely, some of the data are not in sequence with time. So I had to sort that out with so using the data time as the field. I had to sort it with time to make it to make it progress with time, because we're trying to learn from history. We're trying to get a historical pattern to the learn. So basic training. So now, one of the important things about machine learning is something choosing your features carefully, because that determines the prediction of the model. So what I did was to engineer some features from the data set. So there are some things that would increase the variability or increase the predictive the performance of the model. So I mean, things that will affect the amount of energy generated are things like the time of day. So for example, 12 p.m. and 12 noon are two different time, but we expect the maximum or at least a very high power by 12 noon. We also expect very minimum power at 12 midnight because of the availability of the sun. So those are things that affect the model's performance. So one thing I did was get the day of the week, and if it's a weekend, because that affects. Um, then we did an historical from an historical point of view, because we're trying to get from the previous data, how does that affect. Because I mean, it's a forecasting model, so we're using both the current weather conditions and the historical power conditions to get the current or the futuristic to predict futuristic power production. Right, so we did one for 1 day and for 24. Right, 1 hour and 24 hours to get. So since the short time, we're doing on our predictive scale. So we did some other statistic data like the trend, seasonality, and the residual. Right, so those were. So I did drop some data. Right, so I dropped some of the data sets. So I dropped dates because I had extracted the day of the week, and so I don't need them in. Like I said, location and latitude, location, longitude, and latitude are not things. We're not trying to make it dependent on location. We're trying to make it. That's the main point of the project. Trying to make something that can universally work given these conditions. So these are the so pi power is our output. So I moved from my input features and making it the output. So then I splitted data set with a test of 80 and a train of 20%. Then I scaled it to let the features be on the same scale, so that one does not deceive the model that, oh, this is the most important feature. Um, then we trained our model using different models. So the first one was trained through for random forest, because of previous work have said that this had been the best performing model, and I mean we got about 99% accuracy, and it as low as a 0.025 root mean square value, which is a very good performing model, right? So then I tried to compare more. We tried to compare more models to see how they perform each other. So we used k-nearest neighbor, k-nearest neighbor regressor, an artificial neural network, support SVM, support vector regressor, random forest, and linear regression to see how the models perform and compare the results. So in terms of their mean square value, k-nearest neighbor was the worst performing model, but upon further analysis, we saw that the random forest still outperformed the other ones, and is still our best model. Right. So after this, then we brought the input to the optimization function, which I'd working us through now. So for the for the optimization, we so one of the first thing was so for the for the optimization, I had to formulate the model for the model. So the objective function was the loss of load, which is the time or the energy that could not be served. So that the user wanted to serve. So let's walk through the beginning. So for this particular simulation, there were four participants in the network: B1, B2, B3, and B4. Each of them having the same load profile but different PV generation sizing, right? So the main point was for us to add variability in their PV system in the energy availability. So energy PV so user one and user two had less PV generation available to them than their load profile, while user 3 and 4 had more, subsequently more. So in a disconnected network, we'd expect B3 and B4 to have the least loss of load, because they have more energy available to serve their loads, right? But unlike B1 and B2. So The first, so we had to work on the constraint for the battery. So let's go for the first model. The first model is peer-to-peer when all of them are disconnected. So that's a non-sharing model, right? The simulation now the peer to the so why is the desired state of those? So that's the what the user what would the user as his own predefined load profile, what he wants if he has what the amount of load he wants on when he has all sufficient energy. But X is what the user can get. So that's the variable we're trying to optimize, right? So it is the what the optimization function is trying to determine, and that's what the loads that it can serve. So we had to do a constraint such that only the loads that are desired on can be considered on. So we want a case where X the optimization function is turning on a load, right? The load that the user wants off. That would just be a waste of energy and not insufficient. So we had to do so the energy generated by the PV system has to be greater than the energy from the PV system to power the load, and that's to power the battery, right? To charge the battery rather. So each time period the battery is updated, and so we don't want it we are doing this condition such that the battery does not go below a certain threshold of for this particular solution was choosing to be 0.2, right? But all ideal cases were assumed in every simulation. So what we first worked on was setting up each of the users, right? So we set up each of the users, determine their load profile. So show their load profile, right? So these are load matrix for each of them. Like I said, they are the same. So I solved the network in a when peer-to-peer energy trading was not involved. So the result is so it is solving the so the result after this simulation is this. So we can see for B1 that there are more red points. So the red points are the part that we wanted these loads on, but the optimizer could not turn them on because of insufficient energy resource. So for the B1, it had due to its limited energy resource. Excuse me, it had a lot of red point and a few just green points. Green points are the point that we wanted the load on and the load was on, and the blue points are the wanted the load on. Well, we wanted the load off and the load were off. So those ones we don't really care about them, right? So we had more green points, more less green points here. We're trying to reduce the number of red points. So as we move from B1 across to B4, the number of red points decreases and number of green points increases. So intuitive loss of load is decreasing across them. So the higher the energy resource you have, the lower your loss of load, which is what we want in the best case scenario. We cannot always achieve that. So the loss of load in this particular case was about 62,500 watt hour, right? So when we now move to the second case where we have peer-to-peer trading, but with selfless trading. So in this particular case, there is no constraint to when you should sell energy. So you basically if I have energy, any user's energy is not basically their own, which it's not realistic, but it's part of the simulation to see how it affects it. So let's move to that particular case, right? So in this particular scenario where with selfless trading, where the participants are connected, the major change is the introduction of the trading parameter, right? So that's PT. So there was the amount of energy that can charge the battery and be traded to both the battery load balance to the battery power equation to the load power equation, right? Yeah. So one also notable mention is this particular constraint, which is the conservation of energy. So the summation of all the traded energy has to be less than or equals to 0. So because in this particular setup, PT when it's negative is sales and P when it's positive is buying. We do that we look at it more from a consumer point of view. So it has to be sales has to be greater than or equals to the buying if you consider losses, right? So so we ran the same setup, the same load profile for it, and the same generation profile, and the same load matrix. After solution, we can see that yeah, the energy pattern. So there's an improvement in B1 in terms of the in terms of the available energy, in terms of the loss of load. It really went down as across B1 and B2 and B3 and B4 were almost not no change, little change. And one thing that you notice is that the service load is actually similar across all board, because this is because there is no distinction between your own individual energy. So your energy is available to everybody. So this in this way, everyone is trying to share it is shared equally amongst everyone. So in the loss of load, we see that it has gone from 62,000 to 50,800, which is a great improvement. So the loss of load range from 1,400 to 1,100, which is a very little change, and a very little variation compared to the first case, where it moved from 22,000 to 11,000. So there's an improvement. So in the final case, we wanted to make it more realistic as possible, and we tried to factor in some self priority, and this was done by making sure that the participant only trades when he has excess energy, which is by giving threshold. For this particular simulation, the threshold was the state of charge of the battery to be above 90%. So if the battery is not above 90% of this, you don't trade, and that way you prioritize yourself more than before trading. So this was done because using a logical makeshift, because the particular setup is a mixed linear integer programming, which to make a linear logical multiplication of variables would lose its linearity. So I had to make a makeshift constraint for this using logical operations. Right, so the same setup for the participant and network. So let's go to the result. So we can see from the result that now the B1 setup now has more red than the selfless, because this is because the other ones that have excess energy are now prioritizing themselves before they are selling to it, right. So across board, but now B1 B4 has the least red, but not too much compared to the selfless energy. So you can see that this loss of load increases to 53%, not too much, but before went the least. So we can see that from this little demonstration, we can see that when you impute peer-to-peer trading in a network, in a microgrid, the loss of load goes down, which is something we're trying to, which increases energy availability, and that's something that we want in our perfect smart network. So thank you. So with this point, I call us to embrace the new energy dynamics, the new energy topology, and move into a decentralized energy trading system where we can buy, where consumers are transforming into consumers, active participants in the energy generation, and into moving into a greener and more sustainable ecosystem. Thank you.